So we will go over lab 4 and provide some help here for this week's lab on reactions in biology. And so in chapter 5 review, we went over, the types of chemical reactions. Maybe you remember we went over double replacement, and here double replacement are said also to be precipitation, but double replacements can be also acid-base. So double replacement is a more general type of way that two compounds exchange partner. And precipitation is really more specific because it's a double replacement where you are making a solid. So you see here on the product side, you see By is a solid because there is a S in parentheses. So remember how AQ means aqueous solutions, which means it's a solution made of water, and then the compound, the AB compound, for example, is dissolved in that. And that means these are soluble compounds when they are dissolved in water. And so you call that an aqueous solution. And then XY gives a X product, and then the other product is the solid. And that's why this is a precipitation reaction, because you are making a solid from two aqueous solutions, two clear solutions. And the solid will appear like a powder. It will be a fine powder that will make your solution opaque. They will not be transparent anymore. And sometimes they look more like jellified, but often it looks like a powder. And if you give time, they settle down to the bottom of the test tube, for example. So you will see videos of those precipitation reactions, and then you will see videos of oxidation reduction reactions. And oxidation reduction reactions are reactions in which electrons are transferred. So there's many kinds of ways the atoms rearrange, and you will see there will be a single replacement, a combustion reaction, and there was, I think there's another one, it's a gas evolving reaction. So many things can happen when you have oxidation reduction reactions. And then acid-base neutralization is really a more specific type of reaction where you have an acid that can be symbolized by a HX, and those acids are always aqueous solutions. They're always soluble in water, plus MOH. So M symbolizes a metal that is combined with the hydroxide ion. The OH minus ion is the hydroxide ion. It's a polyatomic ion. And these will also be aqueous solutions, but not all of them. So, but when it's aqueous here, it means it's soluble. So when you have an acid and a base that are both soluble in water and you mix them together, the H plus from the acid will combine with the OH minus from the base to form H2O. And then the M from the metal will combine with the, and typically X here would be an halogen. And it will become a salt, MX. Because M is the cation and X is the anion. And sometimes it's not aqueous, that MX can be a solid. So you see many combinations are possible. So here there is a text about balancing chemical equations, and I don't want to go over this. Alka-Seltzer, acid-base, we'll go over this afterwards. And so this is the topic of chapter 7, the solubility. You have not learned that yet, but for this lab, you need to be able to read a table like that of the solubility rules for ionic compounds in water, because I told you some are soluble in water, but some ionic compounds are not soluble in water. And so the way to read this table is that on the left side where it's blue, you have the soluble compound, which means for example, case 1, when you have lithium, sodium, potassium, and ammonium, these will always make ionic compounds that are soluble in water. That's how you want to read this table. When you have, case number 2, when you have the acetate, so C2H3O2 negative 1 is the acetate ion. It's a polyatomic ion. When you have the nitrate, NO3 negative 1 is the nitrate. Or when you have the, let me verify the name of this one. Don't know it by heart. So I'm looking for the list of polyatomic ion here, and ClO4 is the perchlorate with 1 negative charge. So when you have either of these 3 anions, so negative ions here, perchlorate, acetate, or nitrate, you will have always a soluble compound. When you have, so case number 3, when you have the chloride, bromide, or iodide, those halogens, when they are as ions, we call them halides. They are soluble, but there are some exceptions with them. And for example, if chloride, bromide, and iodide are with silver, lead, copper, and mercury, they will be insoluble compound. And you will have some examples of that in this lab. So when they are combined with those, they make insoluble compound. The sulfate always make soluble compound, except when it's with, and here they give the formulas of the compound. Ag2SO4, so with silver, calcium sulfate, strontium sulfate, barium sulfate, lead sulfate, and mercury sulfate are all insoluble. So this tells you the exceptions. And so these are the ions that would mainly make soluble compound, but for a few of them, there are exceptions. And then on the right side, these are those ions that make insoluble compound more generally. Like CO3 negative 2 is a carbonate, make insoluble compounds. CrO4 negative 2, it's the chromate. And then PO4 negative 3 is the phosphate. So the carbonate, chromate, and phosphate make insoluble compound in general, except when they are with lithium, sodium, potassium, ammonium, because these alkali metals always make soluble compounds. So that's why they will not be soluble with them. They will be soluble when they are combined with them, sorry. Case number 2 here in the insoluble compound, S negative 2 is the sulfide ion. Makes insoluble compound except with the alkali metal, Li plus, Na plus, K plus, then the ammonium ion, the calcium, the strontium, and the barium. So all of these will be soluble with the sulfide ion. And then the hydroxide ion, so we were saying earlier that how, the base, when they are symbolized as MOH, aqueous, means they are soluble, but hydroxide tends to make insoluble compound otherwise, except when it's with lithium, sodium, potassium, ammonium. It says here calcium hydroxide, strontium hydroxide, and barium hydroxide appear cloudy due to small amounts of precipitates. So then you don't know what do you do. So when you have a soluble compound, the physical state that you will put in parentheses will be AQ. It means it's soluble in water. Typically, it's we're dealing with water as the solvent. So we say AQ for it's soluble in water. It's forming an aqueous solution. When it is insoluble, like the ones on the left side here, on the right side, make insoluble compound, then you will write that it's S in parentheses. S for solid. So it's easy to get confused because S could be for soluble, but no. S is for solid. AQ is for soluble. Okay, so when it's insoluble, you will write S. When it's soluble, you will write AQ. So that's how we will do that. Hopefully this will not, you see sometimes you will consider them soluble, you know, the calcium hydroxide, strontium hydroxide, and barium hydroxide, and sometimes they will be considered insoluble. So depends on what you do with them. Hopefully there will be no case like that in this lab. So don't forget to put your student name. So there are videos, and they've been combined into a playlist. It's a colleague of mine that does another section of Chem 121 who, you know, put these together. So she has a playlist here that you can access here, but you can access to each video individually also. So you will have to watch videos of, you know, solutions being mixed together and observe what happens. So each time you have a table and it says what are mixed together, the two reactant, and it's given as names. So you will need to change those names into formulas. And so you will watch the video and then write your observations of what happens during that video when you are mixing those two solutions. And here we are in the section precipitation or double replacement reaction, right? So you expect formation of a solid, right? So let's remove that from here and do it again. So I don't want to watch the video with you now. I want you to watch it so that you see what it is observed and then understand what you expect to have to write as observations. And then you want to write the balanced chemical equation. And so from the name, and I think sometimes you are given the name of the product because, you know, we don't expect you to know the formulas. So lead 2 nitrate. So this reviews chapter 3 actually. From the name, we want to find the formula. So lead, if you look at the periodic table, lead is Pb, right? So Pb is in group 4A, right? And that's why you have common, sorry, a Roman numeral. So let me go back here. So that's why you have a Roman numeral, because it's not a predictable ion. But the Roman numeral here tells you it's a 2+, right? The 2 here for as a Roman numeral tells you it's a 2+ ion, right? So you know you have this. And then nitrate. And so if you remember, when the name ends in 8, it's a polyatomic ion. So you will want to go to your list of polyatomic ion, and hopefully you have the reference ready here. So reference information, go to the list of polyatomic ion. So list of common polyatomic ions are there. And nitrogen makes here the nitrate, right? Nitrate, so it's NO3 -1. So you want to copy that next to the Pb2+, NO3. So only the -1 is a superscript and the 3 is a subscript. So I've put them next to each other, positive ion first, negative ion second. Here we can do the crisscross trick. And so the one from the NO3 -1 will be a subscript for Pb. And then the 2 from the charge of Pb will be the subscript for NO3. So we will have only one Pb. And then we will need parentheses because there are 2 nitrates, right? We said two nitrates. Okay. So that's the formula of lead nitrate. And then you want to write in parentheses its physical state. And if you see the video, you will see that it's a solution, right? It's in solution. And we could also go here, PbNO3. So Pb, typically the metals will not be listed except for the alkalis here. So look at try to find the nitrate instead. And here nitrate is here as part of the soluble compound, NO3 -1. So it's a soluble compound and there is no exceptions. So and this would be confirmed by the fact that the lead nitrate would be a solution in the video. So when it's a solution, you say AQ for aqueous solution. It's dissolved. And then sodium iodide. So sodium, hopefully you know by now it's Na, Na plus, right? Because it's an alkali metal from group 1A. So, or as a Na plus as an ion. And then the iodide. And so when it ends in ide, it's normally monoatomic anion, which means you need to look at the periodic table, not the list of polyatomic ion. You need to look at the periodic table, and there iodine becomes the iodide ion, right? When it's just iodine by itself. When the ending of the anion ends in ate or ite, ITE or ATE, it's going to be a polyatomic ion. But when it ends in ide, like iodide, bromide, chloride, fluoride, oxide, sulfide, selenide, phosphide, and nitride. There's not that many of them. I've listed them all. So these are what we call monoatomic ions. They will make a negative ion and there will be just a single atom. If we look here at the list of polyatomic ions, they end in ate or ite, most of them, except, and so that's why I'm insisting on this, because hydroxide is an exception. It ends in ide, but you see there is oxide in there, but there is hydro in front. And so it's hydrogen with oxygen, and that makes the hydroxide ion, right? So be careful, this one ends in ide, but it's a polyatomic ion. And hopefully you want to remember this one from seeing it a lot. Ammonium is different also. This one you kind of have to remember that it's a polyatomic ion. All the others end in ate or ite, except cyanide. Cyanide, Cn-1, is a polyatomic ion, right? So these two, hydroxide and cyanide are ending in ide, and so these are not monoatomic anions. So so we had the Na plus and then I minus, right? We said iodine forms the I-1 ion because it's in group 7A. 7 minus 8 is -1. And so you see that 1 plus 1 minus, they will simply cancel each other out, and the formula is just NaI. NaI, and you need to determine if it's soluble, and according to the video you will see it's an aqueous solution, and so you know it's soluble. But here let's verify. Na plus is part of the soluble compound, and there is never any exception with those. They are always soluble, right? And you can confirm also here with I minus. I minus is also soluble, and Na is not part of the exceptions, right? It's silver, lead, copper, mercury. So we know NaI is aqueous, which means soluble in water. Then you need an arrow. Let me find my arrow. Oops. Okay. So these are the two reactants, and now we need to make products. And here we are in precipitation reactions, and we know these are double replacement, right? They will exchange partner. So that means, and typically those double replacement reactions happen with ionic compound, and ionic compound are made of ions, and typically the ions exchange partner, right? And the positive ions of the first compound will go with the negative ion of the second compound, right? So we'll make Pb, oh, sorry, and their charge doesn't change. So it's still Pb2 plus. You will see that that's very different with oxidation reduction reaction. In the case of double replacement, the charge stays the same on the other side, on the product side. So it's going to be Pb and I minus, because Pb cannot go with sodium, right? Sodium is a positive ion. So Pb will be attracted by the other negative ion that is in solution. And so right now it was with nitrate, but now it will want to go with iodine because it's the other negative ion in the solution. So let's find the formula here. We do the crisscross trick and we see that Pb will be just 1. And then that 2 here will go as a subscript for iodine, and then you drop all the positive and negative charges. Yeah, that's important to completely erase the positive and negative charges once you have the compound formula, because the compound formula is neutral and you shouldn't show any positive or negative charges there because they cancel out, right? It's a neutral formula. That's how we find it. It's because we try to find what will make it neutral. So PbI2 is the one of the product, and now we need to determine its physical state. So let's look at that table here. So PbI2. Again, Pb2 plus is not, listed as a principal ion. It's in the exceptions, though, you will see. So I minus here. I minus is listed among the soluble compound. I minus makes usually soluble compounds, except when it's with Ag plus Pb2 plus. There we go. You see, with Pb2 plus, it's an exception, which means it's insoluble. So when it's insoluble, the physical state you will write is S for solid. Okay? So we are done with this one. And so let's do the other exchange. So when we have a double replacement, again, there is an exchange of ion. And so the cation from the second compound, so always start with the positive ions. So the cation from the second compound will now mingle with the negative ion of the first compound, right? There's an exchange between these two. So Na plus will now go with NO3 negative 1. Right? And it's 1 negative charge here, right? So be very careful. The 3 is a subscript. It belongs to oxygen. It says nitrogen is surrounded by 3 oxygen. And then this whole structure of NO3 has 1 negative charge only 1 negative charge. So that's a subscript. So 1 positive, 1 negative charge. So you see they will cancel out. So you just remove those charges, put them next to each other, or as the positive ion first, then the negative ion. And that makes your formula, the neutral formula. And it's NaNO3. So let's find out its physical state. So go back to that table here. And this one is easy. Na is always soluble and NO3 is always soluble. So both of them are always making soluble compound. And so when it's soluble, we say it's aqueous, AQ, right? So NaNO3 is aqueous. So now we have our product formulas. And so the last thing we need to do, and we already did this, use the solubility chart. You know, you can do in a different order, it's fine. But we should not forget to balance the equation, right? Balancing is part of the writing the equation. So it's, you know, I don't know if I can write below here. So I'll just say it, but here we have one. So remember, when you are balancing polyatomic ions, and here we have one polyatomic ion, the NO3 negative one. So when you're balancing that, you want to keep it as NO3. So maybe, let's see if I write on there. So PB here, I will not write PB. PB, we see there is one on the left, one on the right, right? Na, there's one on the left, one on the right. Iodine, there is one on the left, two on the right. So oh yeah, I don't know. Let's see, like that. So iodine, we have two on the left. One on the, so one on the left, two on the right. I don't know what I said, but it sounded wrong. So one on the left, two on the right of iodine. And then NO3, you want to count it as NO3. Please do not split it. It's not necessary. As I said, when you do a double replacement reaction, the ions stay the same. They just change partners, but they stay the same. NO3 negative 1 stays as NO3 negative 1. You know, the I minus stays as I minus, Na as Na plus, etc. So here you want to count NO3. It's a polyatomic ion that do not dissociate. In solutions, they are very strongly held together. And so how many on the right? We have one on the right. Oops, no. Let's undo that. Okay, one on the right. On the left, we have here on the left, we have two, right? The two here means you have two nitrates. And it's easy to see because there is a parenthesis around them. So it shows what's in the parentheses is 2 times, and so you have 2 nitrates. So you want to balance those two, and the others I didn't write them because they are balanced already. So let's focus on those two. So to balance, typically when you have polyatomic ions, you want to start with them. So let's balance NO3 first. We have 2 NO3 on the left. Let's make it 2 on the right. And to make it 2 on the right, we will multiply, so times 2. Let's make this red. And we will place a 2 here. Why here? Because that's the molecule that has the nitrate, right? The nitrate is in there. So you have to put a 2 in front of the whole molecule. You cannot put it in between Na and NO3, right? It has to be in front of the whole formula of the molecule, NaNO3. And so that will make 2 NO3 on the right, and that balances NO3. And then let's balance iodine. We have 2 iodines on the right, 1 on the left. So we want to multiply by 2 on the left so that we have 2 on both sides. So, and that 2, the coefficient 2 here, will have to go in front of NaI. Why? Because NaI is the molecule that has the iodine, right? So it has to be there to make it 2 iodine. And this way, we have balanced iodine and nitrate. And now if we recount everything, we still have 1 Pb on the left, 1 Pb on the right, 2 NO3 on the left, 2 NO3 on the right. And see, now we have 2 Na on the left and 2 Na on the right. So it balances the Na nicely. And then 2 iodine on the left and 2 iodine on the right. So it is balanced. So that would be the final answer for this chemical equation. So I'll leave this here. And so you have others to do like that, and hopefully maybe you will be faster than what I do here. But okay, so again, you need to watch the video, click on that link, and then write your observations. So please be as detailed as what this one is. You know, just saying red precipitate, I don't know what happens really, but if you say red precipitate, it's okay, but try to be more detailed because probably you can see differences in the behavior between this one and the next, and so try to refine your observation. That's a quality to be able to have observations that are detailed enough that you can see the difference between you know, observations, right? So so iron 3 chloride, find its formula. So again, that's variable charge metal, and the Roman numeral here tells you the charge on the iron. Here, sodium hydroxide, so chloride here. Chloride is made of one atom. It's the chlorine becoming the chloride. But here, hydroxide, even though it ends in "ide", it's a polyatomic ion, and it's the famous OH minus, right? So, and then find your product by doing the exchange of ions, right? Remember, ions are exchanged, but they do not change charge. The charge stays the same. So it's just an exchange. And try to find the formulas of the compounds such that they are neutral formulas. And another example here. So barium chloride. So when you have no Roman numeral here, it tells you it's a predictable ion. And barium is from group 2A, so it's 2 plus. Like sodium is from group 1A, so it's 1 plus. Sulfate ends in 8, so you expect a polyatomic ion here, right? Okay, so let's go through the second type of reactions you will observe. Reduction and oxidation, which is summarized as redox reactions. And you can see here, it says that they can be single replacement reactions. Combustion reactions are a subtype of reduction oxidation. Gas evolving, which means you are producing a gas and it makes bubbles. So these are obvious from the observation standpoint. Decomposition. Decomposition, remember, it's when you start with one reactant and break it apart into you know, 2 or more pieces. So the first reaction will be the single replacement. So do you remember our single replacement? Let me change the share here to my review here. Single replacements are such, here. Single replacement are such that you start with one element, A, plus a compound, BC, and there is an exchange here, but because there is only 3 types of element, you will get a new element and then a new compound, right? So again, there is some kind of exchange happening. And so here you're given the product formulas because this is a transfer of electrons. And so it means here that's very different from the double replacement reaction, right? Single replacement look the same from the standpoint that you are exchanging an element, you know, the compound change because you're exchanging an element. But there is a transfer of electrons and the ions are different afterwards. So it's very different from the precipitation reactions. Because here you start with copper metal. Copper metal is going to be just Cu and a metal by, well, except for mercury, but all metals are solid. So then the physical state will be S. That's so for this you need to decide if it's an aqueous solution or not, or a solid. And for this you will need to look at the solubility rules. Yeah. Let's look at it. Nitrate. And we have already seen nitrate, so we know what it is. It's NO3 -1. So nitrate here makes always soluble compound, right? There is no exceptions. So that means the silver nitrate there will be an aqueous solution. Silver, yeah, I told you that it's an exception among the variable charge metal, among the transition metals, right? If we look at the periodic table. Silver is among the transition metals, right, in the B groups here. It should be a variable charge metal, but it's always making the +1 ion. But here, to simplify things, in the name, they say it's silver 1, so there's no confusion. So find their formulas, arrow, and then here it gives you the name of the product. And so you see how copper was copper metal, which means in its elemental state, and we typically would say it's neutral, it's in its oxidation state of 0. And now it's copper 2, which means copper 2+, right? So that's what is really different with the single replacement reaction. Nitrate stays the same though. Nitrate stays the same. So you will find the formula between copper 2 and nitrate. And then silver now becomes the metal. Silver first was in aqueous, and now it's going to be a metal. It will deposit and form. So silver is, has the silver color, but when it does appear like that, I think it looks more like crystallized. You could almost take it as crystals because it's shiny, but it's not transparent like crystals. So. But with videos it's not always easy to see. So it will become solid. So just AgS, right? A metal is typically solid except for mercury, but all other metals are solid at room temperature when they are becoming just by itself, the atoms of silvers by itself. Okay, so you see how silver was Ag plus here, and now it becomes Ag as a solid, and that's its oxidation state of 0, neutral state, right? So there was an exchange of ions between copper and silver. And so this question here is asking you to determine which one was reduced. Remember how reduced is the one that gain electrons, and which one is oxidized, which means it's the one that lost electrons, right? So which one between copper and silver? So when you're asked that question here, what should be here is only a reactant, right? Don't give me a silver metal, right? Silver metal is a product. It cannot be listed there. Those that are reduced or oxidized are necessarily among the reactants. So either copper metal or silver nitrate. Or just silver, right? Silver 1 here, silver plus. But and so once you find one, then the other will be automatically the other reactant, right? So answer that question. Don't forget to balance your equation and put all the physical states. So here the combustion reaction. I believe I've talked a lot about combustion reaction in chapter 5. Because it's really important you recognize a combustion reaction. A combustion reaction will always need oxygen gas as a reactant. And oxygen gas from the air is O2. It's a diatomic molecule, right? Made of 2 atoms of oxygen bonded together. And the physical state is a gas, right? So for gases, what you put in parentheses is a G, right? ethanol is a compound made of carbon and hydrogen, and it's a gas, so physical state would be the gas. And so when you're burning, because here combustion means burning, right? It's really synonymous to burning. When you're burning a compound made of carbon and hydrogen with oxygen from the air, you always make carbon dioxide gas and water as a gas, right? Because of the temperatures, water will be in its gaseous state. So hopefully by now, maybe you know those formulas by heart. You know, water, you should know. Carbon dioxide, it's 1 carbon, 2 oxide ions, right? So CO2. And all of these are gases. So the physical states should be easy. Then the balancing is more tricky for this kind of combustion reactions. You know, there's more work typically for the balancing. But remember, these are not polyatomic ions, so you need to count every C, every H, and every O. Gas evolving reactions. Here you also have the reactant and the product. So, and it tells you even the physical state here, aqueous. So that means you will write AQ in parentheses. Hydrochloric acid, the formula is given, it's HCl. Yes, because acids are particular in this way that they are, if you look at their formula, H and Cl are non-metals. So they're made of non-metals only. But so because of that, they are covalent compound, right? Made of non-metals only, so they're covalent. But they really behave like if they were ionic. Because here in there, it's H plus and Cl minus when they are in solutions, because it's aqueous. They're always soluble in water. And so in water, they will make H plus and Cl minus. Well, in the case of hydrochloric acid, but acids are particular in the sense that they are, as if you look at their formula, they are made of non-metals only. They are covalent compound, but in practice, they behave like if they were ionic, and they are soluble in water. Aluminum metal, again, when you have a metal by itself, it's just its symbol from the periodic table. And then metals are solid, so the physical state will be S. Here, aqueous aluminum chloride. So, as I said, remember how in oxidation reduction reactions, there is a transfer of electrons. So when aluminum is in its metal state here, it's neutral, it's just Al, and we would say its oxidation state is 0, right? It's neutral. But here, now it's with chloride, and it's an ionic compound, and aluminum is no more neutral, right? So you have to find the formula of the symbol, you know, the symbol of the ion. Aluminum as an ion. Aluminum is in group 3A, so it's a predictable ion. So find its formula when it's with chloride. And then hydrogen gas. Hydrogen gas is a bit like oxygen gas. It's found as a gas and a diatomic molecule. It's H2, right? Hydrogen gas is made of 2 hydrogens bonded together. And the physical state is gas, as it says. So this will require balancing also. And yet another one. So still a redox reaction. This one is the decomposition, which means you have only one reactant, and that's the one reactant. So here the formula is given, so you put that on the left. On the right, you will have water and oxygen gas, and I think we already said what these are. You have to watch the video to know the physical states here. Hydrogen peroxide is a liquid. Then for the physical state of water, you have to watch the video. And there are 2 videos, but this one will not show you really the reaction as, you know, for the observations, you want to watch this one, the one that is there. Okay, and yet another type of reactions, acid-base neutralization, which are double replacement reactions, right? H will combine with OH minus to form H2O, and then the M will combine with the X to make MX. So it's a double replacement reaction. The ions, they keep their charges, right? It's, well, yeah, H plus and OH minus make water. And then the M plus here and the X minus would combine to make the salt. But, you know, this is simplified. This is like a generic way of writing it. It's not necessarily M plus. If you have more than one hydroxide, it may be M2 plus or 3 plus, right? So you have an example of that. Write your observations completely. So here in particular, there may be colors that are shown by indicators. So please write those colors, you know, say the acid is such color by its indicator, and the base has another color, and give the color. And that's due to what we call an indicator. Indicators are showing the pH of the solution, the acidity of the solution in colors. And so, for example, when you change, so if the color changes, it indicates that the acidity of the solution is changing. And you will see that the final solution should have yet a different color, and that indicates, you know, different acidity. And here it's neutralization, so you will see that a bit like with the polarities, green represents the neutrality, I think. So as I said, and I think, yeah, you need to follow this this pattern to find the product, right? And you know already one of the product. One of them will be water, all right? Because when it's acid-base neutralization, you are forming water and a salt. Okay, so that's for the first part of the lab. There's a lot of videos to watch and then observations to write and then the chemical equation. And I think I went over them long enough. So, so the second part is an acid-base reaction where we use Alka-Seltzer tablets that are containing NaHCO3, sodium bicarbonate, also called sodium hydrogen carbonate. There are two names, but that's the same thing. Because if you look at the list of polyatomic ions, HCO3 negative one here is hydrogen carbonate or bicarbonate, right? You can use both names to call it. So when it's with sodium, Na+, it's making the sodium bicarbonate or sodium hydrogen carbonate. Both names are correct. And so let's look at the beginning of the lab because there were explanations about that at the beginning here. Here, the Alka-Seltzer acid-base reaction. Yes, this is about balancing here. So Alka-Seltzer is an effervescent tablet that contains aspirin, acetyl salicylic acid, citric acid, and sodium bicarbonate, NaHCO3. And as soon as the tablet dissolves in water, the NaHCO3 dissociates to form the bicarbonate ion, so the one we saw in the list of polyatomic ion, and the sodium, right? So here it shows how NaHCO3 as a solid, it's a powder or white powder. When you place it in water, because here aqueous means it's now in a water solution, so it would be nice to have water above the arrow here. So when you place this solid in water, it dissociates into the Na+ ions and the HCO3 negative 1 ion. So the sodium and the bicarbonate ion. So you have these two ions floating in solution. And you will place them into acetic acid, right, which is vinegar. Acetic acid is the acid found in vinegar, so like a regular white vinegar. So that's an acid. Acids, you will learn that in chapter 9, but looks like we take a lot of advance here. Donates H+. That's their role. They do that. They donate H+ to water to create H3O+. Right, the H+, grabs on a lone pair of the water, because water, remember, has 2 lone pairs on the oxygen. So it grabs on one of the lone pair and makes the H3O+ ion. And so that makes it acidic, right? The solution will be acidic. And so when you place HCO3 -1, the bicarbonate, if you place it with an acid, so that will contain H3O+, they will combine together, and they will form 2 molecules of water and 1 molecule of CO2, right? That's CO2 here. CO2 is a gas. It's always a gas at room temperature, so it will escape and make bubbles, right? So you will see bubbles forming in the solution, and that's the bubbles of carbon dioxide being formed and escaping, right? It tries to get out of the solution. Notice how the Na+ ions are just what we call spectator ions. They are not involved into the, the actual reaction. They are just floating there, just keeping neutrality for the, with their positive charge. That's it. And so, according to the chemical equation here, 1 mole of HCO3 -1 will react with 1 mole of H3O+ and make 2 moles of water. So here, this is really separated here, 2 moles of water and 1 mole of CO2, right? So it gives you the proportions in which they react. And here there is a word about if the number of moles of each reactant is not the same, then 1 mole will be completely used up during the reaction, while some of the other reactant will remain at the end of the reaction, right? It tells you the fact that if the proportions here, because it's proportions of 1 to 1, so if you have more of one than the other, then that one will stay, there will be some leftover for the one that is, in larger quantity, and the one that is in smaller quantity will be completely used up. And so the one that is completely used up, the reactant that is completely used up, is called the limiting reactant. And so in this experiment, we will have a large excess of acetic acid. So that means we will have a lot of H3O+, and so that will make HCO3 -1 the limiting reactant. And we do that because we want to be able to calculate really how much of it reacted. So we want to make it the limiting reactant on purpose. So if we go here to where you will complete the lab report for this part, there is a video to watch, and it's a professor from South Seattle who made those videos. She shows you how she put, so she has a beaker with 50 milliliters of acetic acid, and actually it's 2 tablets. Here it should be 2 tablets. She will need to add 2 tablets to the beaker. And so you will read, so she has a little balance, and you will read the value here. Then they will react, and there will be some bubbles of carbon dioxide. But the bubbles, they don't want to stay within the liquid. They escape, they move up and go to the surface and then escape in the air, right? So that means you will lose mass from the A to B, you will lose mass, and the mass of the beaker and the reaction after the mixture will be less because you have lost CO2, right? The CO2 gas here does not stay in solution, it escapes. So then the mass will decrease. So, and that difference of mass is only due to CO2 escaping. So that means you will be able to find the mass of CO2 that is released by taking the difference between the mass A and B, right? The difference in mass will be due to the CO2 that has moved out. So that allows you to find the mass of CO2 gone. Then this is stoichiometry. You need to calculate the moles of CO2 gone by using the mass. So to calculate D here, you need to take the mass of CO2 as your given amount, and then the moles of CO2. To calculate from grams to moles, remember you need the molar mass, right? So you will need the molar mass of CO2. Next, using the equation here, calculate the moles of NaHCO3 that has reacted. So notice how 1 mole of NaHCO3 will give 1 mole of CO2. So that means the moles of CO2 released will be equal to the moles of NaHCO3 that reacted. But you will need to show that in question 1, right? By showing the mole-to-mole ratio, the equality that says 1 mole of CO2 is produced from 1 mole of NaHCO3, right? We want you to show that. And then from the moles of NaHCO3, you will calculate the mass. And again, that to go from moles to mass, you need the molar mass. But this time it's the molar mass of NaHCO3, right? So you will need the molar mass of NaHCO3 and use it as a conversion factor to change moles to mass. And those calculations you will do between C and F here will need to be shown here in question 1, right? So it could be just one big calculation that uses the mass of CO2 as the first, the given amount, that has 3 conversion factors to show how first you change it to moles of CO2, then moles of NaHCO3, then mass, right? It could be the final calculation here that shows the 3 conversion factors multiplied together. It's okay to do it this way. So for those of you who are able to, if your computer allows it, you can do like me and insert an equation here, right? I don't know, like, let's say 4.5 grams of CO2. I was going to show an equation here. 4.5, no, it doesn't work. Oh, okay, right, you can do that, and that will allow you to show it in the proper format, right, where you use those times, and then the conversion factors will be shown as ratios like that. So you can use that instead of taking a picture of your work on paper. It's up to you. Which way is easier, you should go for it, because I don't want you to waste time with formatting if it's not easy for you to do. I don't know, in Google Doc, for example, I actually don't know if it's easy or not to do this. Okay, so there are 4 questions. That's the first question, showing the work. Here, the Alka-Seltzer packaging state that it's 1,916 milligrams of NaHCO3 in each tablet. In this experiment, we will use 2 tablets. So basically, you just add the, or multiply this by 2. Here, because we are dealing with grams, this is going to be in grams here. The G's here are for grams, not gas. So maybe you want to convert that to grams. I think that would be a good idea to have this in grams, the total mass. Because then here, to calculate the percent of NaHCO3 that has reacted in the tablet during the experiment and compare it to the amount stated on the package, you will need to take the amount you found in question 1, or that is here in the table F, right? Value F is the mass that reacted, and you want to compare it to the mass that is stated on the package, right? So it's going to be, it's kind of the percent yield, where you take the actual yield, except that we cannot really call it a yield because NaHCO3 is a reactant. So it's not really a yield, it's more what reacted. So you want to take the amount that reacted that you found in F here, line F, over the amount that is theoretically in the tablets, times 100, right? That's what you want to do here when it's asking, calculate the percent of NaHCO3 that reacted in the tablet during the experiment compared to the amount stated in the package. So times 100 and find the percentage. And so the percentage may be, of course, it's not going to be 100, it's going to be more or less. And so you want to discuss here what it means if it's more than 100% or if it's less. So if it's less, it means less than what was in the tablets reacted. But if it's more, more than what was in the tablet reacted, that's also possible. But then that means there is, you know, errors, or because we had to do this at home, you know, it was not done in a lab with materials that allow us to do precise measurements. So that can be a reason why you will find that it's much more, for example, right? Because the balance the professor used can only read to 1 gram. So that really limits the amount of mass change that you can observe. Okay, so that's what Lab 4 is about. So do you have any questions? I know I've talked a lot. So I can take your questions on Wednesday for during next Zoom meeting, or by email. If you have questions, send them by email. But I would advise you to try to do the lab for before Wednesday, so that if you have questions, you can ask them on Wednesday's next Zoom meeting, especially that the lab is due on Wednesday night. Okay, so you're welcome to send your questions otherwise.